Okay, let's continue our class. Um, Next, we will discuss about composite functions. Um, First of all, what is the definition of composite functions? We have two functions, fx and gx. Then we call gfx. Right now, fx is the variable of gx, or we can also call fgx, where gx is the variable of fx. So both functions are composite functions. Remember that for the first composite function gfx, fx is the variable of gx. We just substitute the x in gx by fx, and in the second case we have fgx. Here gx is the variable of fx. We just substitute x by gx in fx. So uh, then here we have some examples. For example, we have fx is equal to square root x, and gx is equal to x squared plus 1. Then for gfx we have f squared plus 1, and because fx right now is the variable of gx, we just substitute x in gx by fx, and then we got square root x squared plus 1, and finally we got gfx is equal to x plus 1. We also have fgx is equal to square root g, and then is equal to, we just substitute x of fx by gx, and then we got square root x squared plus 1, and finally the result is square root x squared plus 1. This is the function of fgx. Um, from this from this example, we have a byproduct. So we note that in general, fgx may not be able to be equal to gfx. So fx may not be equal to gfx. May not be equal to gx. Just remember. Then we have order functions and even functions. Composite functions are very simple, and then we come to order functions and even functions. Given a definition, if given a function fx, if f minus x is equal to fx, what's next? For all x, fx is even. How about order function? Given a function fx, if we have f minus x is equal to minus fx for all x, f will be odd function. So in geometry, an even function is symmetric about the y-axis. About the y-axis, you can have a look at this sketch. An even function, this is an even function. You can check that given a minus x, for example here, the f minus fx is equal to fx here, right here. And we can also have fx. We can also have an order function. So in geometry, An odd function is symmetric about the origin. So you can have a look at this the right hand side sketch. Given minus x, for example here, we can get the function f minus x is symmetric about the origin to this one, f x. We just, for example, at this moment um, we just rotate the sketch of the function, and then we got exactly the same function, same sketch. If we rotate the if we rotate the sketch by according to the origin. Many functions. Here I give you one piece of our experience, and you just keep in mind. Many functions are neither odd nor even. Neither odd nor even. I give you some example. I just give you some example. Are the following functions even, odd, or neither? For the first one, fx is equal to x squared plus 3. Is this odd function, even function, or neither? Can you tell me? Let's have a check together. Okay, now fx is equal to x squared plus 3. We just check f minus x, and then we got f minus x squared plus 3, and at this moment minus x squared is equal to x squared plus 3. So f minus x is equal to fx. This is an even function. The next one, fx is equal to x plus 3. Because f minus x is equal to minus x plus 3, so, and f minus x is not equal to fx, and it's not equal to minus fx as well. So the result, function fx neither. Fx, so the third one, fx is equal to 2x cubed minus 5 over x. How about this one? You can calculate it and to see whether we have the same result. My answer is odd function. Why? Similarly, we just check f minus x. For f minus x, we have 2 minus x cubed minus 5 over minus x. And finally, we got f minus x is equal to minus fx. So this is an odd function. This is an odd function. We also have fx is equal to x cubed plus x to 5 plus 3x. We just check f minus x, and we can find that f minus x is equal to fx. You can have you can have a try by yourself. You can have a try by yourself and to see whether f minus x is equal to fx. Here, my answer is because fx f of minus x is equal to fx. This is an even function. The fifth one, also the last one, we have fx is equal to x over x cube plus 1. We just check whether f minus x is equal to fx. And finally we found that for this function, f minus x is not equal to fx, and it's also not equal to minus fx. So neither. One-to-one functions. One-to-one functions. What is one-to-one functions? What is one-to-one function? Given fx, if this function is a one-to-one function only if for each possible y we have exactly one x value. So let's recall the definition of the function of a function. So what is a function? Function is given a x, there is exactly one y, but it cannot make guarantee when there is a y we have exactly one x value. So reversely, it may not be supported. So for one-to-one function, we just restrict that this is a function, and then we also need to make sure given a possible y we will have exactly one x value. So given a function, no matter we reverse we have a reverse thinking. So given an x, we will have a one y, and given a y, we will have one x. Very restrict. Have a look at the sketches here. On the right, on the left-hand side, this is a one-to-one function, but on the right-hand side, this is not. Why? Because we can just use a horizontal line which is parallel to the x-axis, and that line will intersect with the sketch by 2 points. This means given a y, we may have two different x's. So this function, the function on the right hand side is not a one-to-one function, while the left hand side the function is a one-to-one function. How to prove a function to be a one-to-one function? Because sometimes sometimes it's very difficult for us to sketch. It's very difficult for us to sketch a function so that we may not be able to see and determine a function to be one-to-one function or not, because we cannot sketch it. So at this moment we will rely on algebra. Algebraical method. Give me a one-to-one function. We just write fa is equal to fb, and we try to solve a. If a is equal to b is the only solution, y will be a one-to-one function. Otherwise, this function is not a one-to-one function. So here we have an example. Remember this method, okay? Remember this method. method. We just write fa is equal to fb to check whether a is equal to b is the only solution for this equation. If it is, so the function will be a one-to-one function. Otherwise, f is not a one-to-one function. We have an example. We just use algebra that the following functions are one-to-one function or not. So we have y is equal to fx is equal to x squared plus 7. We just check that fa is equal to fb or not. If it is, f squared plus 7 it will be equal to b squared plus 7. Then we have a squared will be equal to b squared. And then we have a is equal to b or minus b. At this moment, because a is equal to b is not the only solution. It's not the only solution. This function is not a one-to-one function. It's not a one-to-one function. Let's come to the next example. Let's come to the next example. Fx is equal to the modulus of 2x minus 1. We just write, because we want to check whether a is equal to b is the only solution of fa is equal to fb. So we just have the modulus of 2a minus 1 is equal to the modulus of 2b minus 1, and then we solve the modulus. Then we will have 2a minus 1 is equal to 2b minus 1 or minus 2b minus 1. And then we will have a is equal to b or a is equal to minus b plus 1. At this moment, a is equal to b is not the only solution, so f is not a one-to-one function. We just sketch it. We just sketch both functions. On the left-hand side, we have the sketch y is equal to x squared plus 7, and on the right hand side we have y is equal to the modulus of 2x minus 1. And for these two functions we found that they are we just use a horizontal line to intersect with the sketch, and we found that there will be 2 points. There will be 2 points in the intersections. So this is not a one-to-one function. This is not a one-to-one function. Okay, let's come to the inverse function. The inverse function. The inverse function is an extension. Is an extensive the concept of one-to-one function. Given fx, if fx is 1-to-1, then x and y can be swapped to give x is equal to fy. Solve this equation for y gives a new function, the inverse functions denoted by y is equal to f minus 1x. So it's very simple. We just giving fx, we just just substitute x by y and substitute y by x, and then we solve the new y and we will get the inverse function. The f okay, for the inverse function, we just want to make sure that f minus x does not mean 1 over fx. Okay, for 1 over fx, the minus 1, the power of minus 1 will be right to the corner, not in the middle. Okay, we have a here I give you several examples. We want to find out the inverse function of the following one-to-one function. We have fx is equal to 4x minus 7, and since y is equal to 4x minus 7, we just swapping x and y, it will give x is equal to 4y minus 7, and we solve y, and if we want to solve y, we will get y is equal to x plus 7 over 4, and then we can get the inverse function to be x plus 7 over 4. In the second example, we have y is equal to x cubed. We just swapping x and y, it gives x is equal to y cubed. Then we will get y is equal to x 1/3. Wait, x to 1/3. The inverse function will be x to 1/3. So, um, if and right now we understand that the inverse function is based on the one-to-one function. But given a function, if it's not one-to-one function, and you know we want to get the inverse function, what should we do? We will restrict. Okay, we will have to restrict the domain and make sure we got a partially, one-to-one function, and then we will get the inverse function. We'll get the inverse function. So in geometry, what are the reflections of each other in a line y is equal to x? What are the reflections of each other in line y is equal to x? So we have here we just give you an example. We have fx is equal to 4x minus 7, and we can also get the inverse function of the original function as x plus 7 over 4. Okay, so first of all, we needed to find out the intersections. We just said that fx is equal to x, and then we have 4x minus 7 is equal to x, and finally we got x is equal to 7 over 3. Just got 7 over 3. And you can substitute x is equal to 7 over 3 into fx, and the inverse function of fx, that is f minus x. You just substitute x by 7 over 3 to see whether fx is equal to f minus x. sure you can get it. It's equal to each other. It's equal to each other. Some students may feel confused that why not to, in order to find the intersection, why not to use fx is equal to f minus x. Here I recognize just a simplicity. If we check fx is equal to x, it will normally the equation will be very simple. Will be very simple. Okay, so that's all for the second class.